Okay, that's so much about hydrogen power. Let me now say a few words about biofuels. And the first lesson here is that despite wondrous progress in batteries and visions of all electric vehicles, it's pretty damn hard to beat liquid hydrocarbons for energy storage. This chart shows the energy density of various forms of fuels for vehicles. Gasoline is that red dot on the upper right. Diesel would be about the same. The best batteries that we can build now are that gray dot down in the left-hand corner, okay? 50 times. Now, it is true that electric motors use the energy in batteries much more efficiently, and there is regenerative braking that you can apply to save energy in a vehicle and so on. But you should also realize that internal combustion engines can be made much more efficient than they are right now. Typical internal combustion engine efficiency is 25%. That can easily be increased to 35%. It's all a question of how much do you want to pay. Right? Just in the same way that the electric vehicles are a question of how much do you want to pay. And you can bet that the automotive companies, maybe not those in Detroit, but certainly those in Japan, are working on improving those efficiencies. My guess is that the future is going to be plug-in hybrids, at least for a long while. And certainly liquid hydrocarbons are going to be an important element of making that work. So the question is, where do you get your liquid hydrocarbons from? As we surveyed the possible sources beyond petroleum, there was coal to liquids, which is bad because it makes more emissions than just plain old petroleum. Advanced biofuels was really the only thing that could simultaneously satisfy in a material way both greenhouse gas criteria and security of supply criteria. Notice I say advanced biofuels. Conventional biofuels, as practiced in this country by corn ethanol, have many drawbacks, not the least of which, as was already mentioned either today or yesterday, they cannot scale to materiality. What do we have to do? And the answer is we have to take the petroleum value chain, which has been practiced for 150 years by companies like BP and Exxon and Mobil, Shell, which starts from finding the petroleum, through refining it, transporting it, and making it into a real fuel. That chain has been optimized to better than the 1% level by 150 years of experience at, of course, business necessity. We've got to take that chain and somehow fuse it with the agricultural value chain, which is several thousand years old and works very efficiently, and create something new. Something that starts from the germplasm. What plants do we grow for energy? They're different than the food. How do we grow those plants sustainably? How do we harvest and process them? How do we decompose the lignocellulose, which is intrinsically refractory material because it's what makes the plant stand up and what makes it resistant to pest attacks? And how do we process the sugars that result from that decomposition of cellulose into a real fuel that's much better than ethanol or even butanol, which we are also trying to do in partnership with DuPont. There is a whole set of technologies to develop here and extraordinary cross-optimizations across the chain to be realized. And if you do the back-of-the-envelope numbers, there is plenty of land and water in the world to satisfy a material bit of the fuel demand and still produce the food that we need in a sustainable way. If you think more broadly about the intersection between energy and biology, there are powerful reasons why that should be a very fertile intersection of needs and technology. One is that biology, and I had the privilege of watching science for more than a decade, helping to run Caltech, watching the whole spectrum of science and engineering. And biology, I can tell you, was and remains the most rapidly evolving of the sciences, and you know that novel technologies emerge from rapidly developing science. And therefore, you can guess that biology will generate disruptive technologies, as it is already doing in the life sciences. The second point is that 90% of the world's primary energy, mostly fossil fuels, but 10% biomass, are based upon carbon. They're not called fossil fuels for nothing. They were once living. And so you might think that 3.5 billion years of evolution would have something to teach us about handling carbon. So there are likely to be great synergies between energy and biology. And finally, major funding for biology and biotechnology has been in the biomedical and biotech areas. There have been far smaller investments in agriculture, materials, and chemicals. This is largely white space, to use the jargon of your community, I guess. Right? And so we're looking at applications that are most immediately biofuels, but enhanced oil recovery, the conversion of carbon using biological or biologically inspired means, and carbon sequestration are all opportunities where biology can play. For various reasons which I don't have time to go into, BP chose to establish something called the Energy Biosciences Institute to pursue these opportunities. It is the world's first dedicated research organization that's trying to explore the application of biology to energy issues. Let me close by saying that energy is only the most immediate manifestation of a whole host of problems that I believe we are going to be facing in the next several decades, driven largely by the rise of a third of humanity economically. Energy, water, food, land, metals, all of these are going to be issues that combine technology, economics, politics in a global way. There will be no easy solutions. But I think understanding how we mix big businesses, small firms, academia, and government to think through and start to implement some of those solutions is going to be the defining challenge for the next couple decades.